Linear Algebra, Lecture 7. And let me look at a couple of the problems on the review sheet. Problem 1a. We have three vectors, 0, 5, 3, 3, 0, 5, and 3, 3, 0. And we want to know if these vectors are linearly dependent or linearly independent. So we need to know, find scalars x1, x2, x3, such that x1 v1 plus x2 v2 plus x3 v3 is the zero vector. And if there's a choice of scalars that's where the scalars are not all zero, if this is a non-zero vector, then these v1, v2, v3 are linearly independent. So x1 v1 plus x2 v3 plus x3 v3, that's x1 times 0, 5, 3 plus x2 times 3, 0, 5 plus x3 times 3, 3, 0. Let's see, this is 0, 5x1, 3x1 plus 3x2, 0, 5x2 plus 3x3, 3x3, 3x3. When you add this all up, you get the vector 3x2 plus 3x3, 5x1 plus 3x3, 3x1 plus 5x2 plus 3x3. And we want to know for what vectors x1, x2, x3 is this equal to 0, which is the same as solving three equations and three unknowns. 3x2 plus 3x3 equals 0. 5x1 plus 3x3 equals 0. 3x1 plus 5x2 equals 0. And how do we solve these equations? Well, you can solve it any way you like. For example, if you subtract the second equation, if you subtract the first equation from the second, you get 5x1 minus 3x2 equals 0. And the third equation is 3x1 plus 5x2 equals 0. If you multiply the first equation by 5, and the second equation by 3, and if you add, the x2's cancel, you get 34x1 equals 0, which means x1 has to equal 0. If x1 is 0, x3 is 0, and if x1 is 0, x2 is 0. So the only scalars, the only vector x1, x2, x3, where this linear combination is 0 is the trivial linear combination. So that means these vectors are linearly independent. The method of solving these three equations and three unknowns, it's up to you. I just did it by simple Gaussian elimination. You could also write down the matrix and put it in reduced row echelon form. Any way you want to do it is okay. Problem is to find out if the vectors are linearly dependent or independent or not. Let's look at problem B. So this is 1b. Here we have the three vectors. v1 is 5 minus 2, 1. v2 is 1 minus 2, 5. v3 is 1, 1 minus 4. And if we want to solve the equation x1 v1 plus x2 v2 plus x3 v3 equals the 0 vector, that's equivalent to saying that you do multiply this by x1, this vector by x2, this vector by x3, you get 5x1 plus x2 plus x3 minus 2x1 minus 2x2 plus x3, x1 plus 5x2 minus 4x3. We want to know when is that equal to the 0 vector. So we're solving three equations and three unknowns. Let me do it by using the matrix. So the coefficient matrix is 5, 1, 1. I could add a column of zeros, but I don't have to because that's going to stay 0 no matter what. But it doesn't hurt if I do it. Minus 2, 1, 1, 5, minus 4. So I want to put this matrix into reduced row echelon form. So I could divide the first row by 5, but I get some fractions. It's easier to get a 1 here by interchanging the first and the third rows. So 1, 5 minus 4 switches with 5, 1, 1, and the middle row doesn't change. And then I want to get zeros in this first column under the 1. If I add 2 times the first row to the second row, I get 2 minus 2, 10 minus 2, minus 8, plus 1. If I subtract 5 times the first row from the third row, 5 minus 5 is 0. 1 minus 25 is minus 24. 1 plus 20 is 21. I have 1, 5 minus 4, 0, 8 minus 7. I notice if I add 3 times the second row to the third row, I get 0, 0, 0. And I could almost stop there, but then I keep going. So 1, 5 minus 4, 0, 0, 0. I want a 1 here, so I divide this by 8. So I get 0, 1, minus 7/8. And then I get 0, 1, minus 7/8, 0, 0, 0. If I subtract 5 times the second row from the first, I get 1 minus 0, 5 minus 5, minus 4. If I multiply this by minus 5, that's 35 over 8. 35 over 8 minus 4 is 3 over 8. So this matrix is now in reduced row echelon form. So the original system of equations is equivalent to x plus x1 plus 3/8 x3 equals 0, x2 minus 7/8 x3 equals 0. So x1 is going to be minus 3/8 x3, x2 is going to be 7/8 x3. So any vector for any value of x3, by that x1 be minus 3/8 x3 and x2 be 7/8 x3. Any scale x3 times any minus 3/8 7/8 1. This is a solution of the system of equations. So with these values of x1, x2, x3, the linear combination of v1, v2, and v3 is 0. So these are vectors that I started with are linearly dependent. And let's just check. Suppose I take this vector and I multiply it by 8 to get rid of the fractions. I'd have minus 3, 7, 8. So let's see. Minus 3v1 plus 7v2 plus 8v3. This was my original set of vectors. So that's minus 3, 5 minus 2, 1, plus 7, 1 minus 2, 5, plus 8, 1, 1, minus 4. This is minus 15, 6, minus 3, plus 7, minus 14, 35, plus 8, 8, minus 32. And you'll see when you add these vectors, you get 0, 0, 0. So here are my vectors v1, v2, v3. I'm taking this linear combination of them. I get the 0 vector. So that's as concrete a proof as you can ever find that a set of vectors is linearly dependent. Problem 3, we take a set of vectors S consisting of 1, 1, 1, 2, 2, 1. So this is a set of vectors R2. Now we know that the dimension of R2 is 2. And the cardinality of the set S is 3, which is bigger than 2. A set of dimension n cannot have more than n linearly independent vectors. So we know instantly that S must be linearly dependent. In fact, if we look at this, we notice if we add the second and third vectors, you get 3, 3, which is 3 times this. So you can just observe that minus 3 times the vector 1, 1, plus 1 times the vector 1, 2, plus 1 times the vector 2, 1 is 0, 0. So I have this linear combination with coefficients 3, 1, and 1 that gives the 0 vector. So it's clear these 3 vectors are linearly dependent. But let's say, what about if I take 2 of them? So suppose I take the vector 1, 1 and 1, 2. Are those vectors linearly dependent or linearly independent? So if I take x times the first and y times the second, it gives me the vector x plus y, x plus 2y. These are linearly dependent if I have x and y not both 0, where this vector is 0, 0. That means we have to satisfy the 2 equations, x plus y equals 0, x plus 2y equals 0. If I take these 2 vectors and subtract the first from the second, I get y equals 0. Y is 0, x is 0. So these 2 vectors, 1, 1 and 1, 2, are linearly independent. So they generate a 2-dimensional subspace, and so the subspace generated by S has dimension 2. And it's contained in a vector space of dimension 2, and therefore has to be equal to that. So the subspace generated by this set S is R2, and this is a basis for it. That's problem 3. There's nothing more important to understand in the beginning of linear algebra than dimension. And the main theorem, which I proved, and I'll just keep repeating it, says the following: let V be a finitely generated vector space over the field F. The field F can be any field, real numbers, complex numbers, something more exotic. Finitely generated means there is a finite set S whose linear combinations give you all of V, a finite set of vectors, a subset of V. And the linear combinations of the vectors in that set give you the entire vector space V. There exists a finite set B contained in V such that V generates the vector space V, and the set of vectors in V is linearly independent. Every such set B has the same number of elements, and this number is called the dimension of V, denoted dim of V. So this is really, and the set V is called a basis for the vector space V. And so the simplest and the most important example is the vector space V is Rn, and the set B consists of n vectors. Dimension of V is n, and V consists of n vectors E1, E2, up to E sub n, where E sub I, well, E1 is the vector 1 and then all zeros. E2 is 0, 1, and then all zeros. E3 is 0, 0, 1, and then all zeros. And in general, the vector E sub I is the vector with zeros, then a 1, and then zeros. And this, the number 1 occurs, it's the ith coordinate. And one can also write this vector EI as delta I1, delta I2, delta II, delta IN, where delta IJ is defined to be 1 if I equals J, and 0 if I is different from J. And this function, delta IJ, is called the Kronecker delta, which we see all the time in mathematics in general and linear algebra in particular. It's a very useful notation. This is what is called the standard basis for Rn. And if we take any vector x in Rn, say x is x1, x2, x3, down to xn, I can write this as a sum of n vectors, x1 and then all zeros, 0, x2 and then all zeros, 0, 0, x3 and then all zeros, and so forth, up to 0, 0, and then lasting with xn. You add these n vectors, you get this. And this is exactly the same as x1 times the vector with 1 and then zeros. And x2 times the vector 0, 1, and then zeros. And x3 times the vector 0, 0, 1, and then zeros. Up to x of n, up to xn times the vector zeros and then ending in a 1, which is x1 e1 plus x2 e2 plus x3 e3 up to xn en, which if I like, I can write as summation I goes from 1 to n, xi e sub I. That's the vector x. So the standard basis is e1 up to en, and I can write x as a linear combination of the out vectors in that basis, and the coordinates are simply the coordinates of x in the usual representation. So for example, in R2, any vector x1, x2 is x1, 0 plus 0, x2. That's x1, e1 plus x2, e2. Where we're taking our basis to be e consisting of the vectors e1 and e2. Suppose I take a different basis. Suppose I take the vector f1 to be 2, 3, and f2 to be the 1, 2. I claim f equal to the vector f1, f2 is also a basis for R2. Let's check. I have the set F consisting of the vectors 2, 3, and 1, 2. Let's call this F1 and this F2. First, I need to prove they're linearly independent. This is certainly contained in R2. These are two-dimensional vectors. x1, f1 plus x1, f1 plus x2, f2 is x1 times 2, 3 plus x2 times 1, 2. If I write that as a single vector, that's 2x1 plus x2, 3x1 plus 2x2. And I want to know for what x1 and x2 does this give me the 0 vector. So I have to solve two equations and two unknowns. 2x1 plus x2 equals 0. 3x1 plus 2x2 equals 0. And you can solve these equations, that's high school algebra, and the only solution is x1 equal x2 equals 0. So these vectors are linearly independent, so F is a basis for R2. So every vector in R2 is a linear combination of F1 and F2. Suppose I want to write the vector E1. Remember, the standard basis consists of vectors E1 and E2, where E1 is 1, 0, and E2 is 0, 1. So I can write E1 as some linear combination of F1 and F2, and I can write E2 as some linear combination of F1 and F2. So I want to find these numbers. This is 1, 0 is P1, 1. What was F1? 2, 3. And P2, 1 times F2, 1, 2. Let me see if I can solve these equations. So this is 2 P1, 1 plus P2, 1, 3 P1, 1 plus 2 P2, 1. Here, E2 is 0, 1. Is this linear combination, which would give me P1, 2, 2, 3 plus P2, 2, 1, 2. This is 2 P1, 2 plus P2, 2. 3 P1, 2 plus 2 P2, 2. So I want to solve the equation. So let me just use use X and Y for the moment. Here I'm solving equations 2x plus y equal 1, 3x plus 2y equal 0. Here I'm solving the equations 2x plus y equals 0, 3x plus 2y equal 1. So in both cases, I'm trying to solve something like 2x plus y equals let's call it R, say. Three x plus 2y equal s. So if I have two equations and two unknowns like this, these are inhomogeneous equations. I want to solve these equations for x and y. It depends on R and S, but let me solve it for x and y. So this is just like what we did at the very beginning of the course. We're simply solving two equations and two unknowns, right? That's what you learned how to do in high school. 2x plus y equals R, 3x plus 2y equal s. So if you write down the augmented matrix, and then you do elementary row operations to get it in reduced row echelon form, we'll find x and y. The augmented matrix is 2, 1, R, 3, 2, S. So I want to put this in reduced row echelon form. I can divide the first row by 2. I can then take the second row minus 3 times the first row. 3 minus 3 is 0. 2 minus 3 halves is a half. S minus 3R over 2. I can then multiply the second row by 2. And then I can, S minus 3R. S minus 3R. I take the first row minus half of the second row. 1 minus 0 is 1. A half minus a half is 0. R over 2. Let me just leave this up here. I have R over 2 minus a half S minus 3R. That's minus a half S. 3 halves R minus 1 half R is R. second. S minus 3R minus a half S R over 2 plus 3R over 3 halves R. 1/2 R plus 3 halves R is 2R. So this is 2R minus 1/2 S. So this says the solution of these two equations and two unknowns is x equals 2R minus a half S and y equals S minus 3R. So let's just check. If we take R equal 1 and S equals 0, we get this vector xy, if you like, or xy. Just R is 1. This is 2 minus 3. So what that says is that two times f1 minus 3f2. f1 was the vector 2, 3, and f2 was the vector 1, 2. So that's 4, 3, 4, 6 minus 3, 6 is 1, 0, which is E1. So that's perfect. And if I take R equals 0, S equal 1, I get xy, R is 0 and S is 1, is minus a half 1. So if I look at minus a half f1 plus f2, this is minus a half. f1 is the vector 2, 3. f2 is the vector 1, 2. So this is minus 1 minus a half times 2 is minus 1. Minus a half times 3 is minus 3 halves. Plus 1/2. We have a little problem. This is, 1, 2. This is 0 1/2. So I'm off by a factor of 2. So I have to figure out what I did wrong. So I take the matrix. I have to solve these two equations and two unknowns. 2x plus y equal r, 3x plus 2y equals s. This is the augmented matrix, 2, 1r, 3, 2s. It gives me a half. It gives me 1/2 r over 2. Then 1/2 r over 2. I take minus 3 the first row plus the second. Minus 3 plus 3 is 0. Minus 3 halves plus 2 is plus a half. Minus 3r over 2. Oops, maybe my error was just sloppy writing. This is s minus 3r over 2. Then I take the second row and I multiply it by 2. So I get 0, 1, 2s minus 3r. And the first row is 0 1/2 r over 2. So I have 0, 1, 2s minus 3r. And I take the first row minus a half times the second row. So that's r over 2 minus a half 2s minus 3r. So that's r over 2 plus 3r over 2, which is 2r, and minus a half times 2s is minus s. So this should be just be minus s. So if r is 1 and s is 0, this is still 2 minus 3, so this worked. If r is 0 and s is 1, this is minus 1, 1. Perfect. Minus 1, 1. And minus f1 plus f2 is minus 2, 3 plus 1, 2 is still wrong. I'm getting, this is really interesting. So I have the vector 2, 3, the vector 1, 2, and I want to find a linear combination of them that equals the vector rs in general. So 2, 1r, 3, 2s, 1.5r over 2, 3, 2s, 1.5r over 2, 3 minus 3 is 0, 2 minus 3 halves is a half, s minus 3r over 2. Multiply the second row by 2, 0, 1, 2s minus 3r. I take, and then I take the first row minus a half the second row. So this is 0, 1, 2s minus 3r, r over 2 minus s plus 3r over 2 is 2r minus a half times this plus this. I get minus s minus a half times minus 3 is 3 halves plus a half is 2. 2r minus s. Okay. So this looks pretty good. 2r minus s, oh, sorry, 2s minus 2r. Okay. So when r is 1 and s is 0, this is 2 minus 3. But when r is 0 and s is 1, this is minus 1, 2. So minus f1 plus 2f2 is minus 2/3 plus 2 times 1, 2. This is minus 2/3 plus 2, 4. And 2, 4 minus 2, 3 is 0, 1, which is E2, which is exactly right. So that's pretty good. Let me just write that down for future use. So we have E, the standard basis consists of the vectors E1, which is 1, 0, and E2 is 0, 1. And we have another basis F consisting of vectors F1 equal to 2, 3, and F2 equal to 1, 2. And we have a relationship between them, namely E1 is 2f1 minus 3f2, and E2 is minus F1 plus 2F2. So we might want to keep that in mind for future use. Now, suppose, so we have two different bases, E and F, for R2. Suppose we take a vector V equal, let's say, xy in R2, which means V is, in terms of the basis E, xe1 plus ye2. That's x times e1, which is 2f1 minus 3f2, plus y times e2, which is minus f1 plus 2f2. So V is equal to, it's a linear combination of f1 and f2, 2x minus y, f1, plus minus 3x minus y times f2. Let's just analyze this a little bit more because it's interesting. We have this vector V. Its coordinate vector with respect to the basis E is xy, xe1 plus ye2. But its coordinate basis with respect to the basis F is 2x minus y minus 3x minus y. We could write this relationship as a kind of a matrix. Suppose we consider the 2 by 2 matrix P, and I want P to have the property that applied to xy, the vector xy, we get this vector, 2x minus y. This has to be 2 minus 1 minus 3 minus 1. Let's see whether this is correct. This is 2f2. So this is 2x plus minus yf1 minus 3x plus 2yf2. This is 2. So P times the vector xy is the vector 2x minus y minus 3x minus y, which is the coordinate vector for V with respect to F. This is the coordinate vector for E with respect to, for V with respect to E. So if these, so this is what we call a change of basis matrix. So if you have the coordinates, if you have two bases, E and F, for a vector space, if you have the coordinate matrix for a vector with respect to one basis, if you multiply it by this matrix P, you get the coordinate vector for the base, for the coordinate vector for the vector V with respect to the basis F. And what I want to do is just explain how this works in general. That's the important. So we say let V be a vector space over a field F. The dimension of V is equal to n. So every basis consists of n vectors. Suppose we have F be this ordered sequence of vectors F1, F2 up to F sub n, and G, another sequence of n vectors, G1, G2 up to G sub n, be bases for V. Now, let V be any vector in the vector space V. Then V is some linear combination of the vectors in a basis. Say this is summation xi f sub I goes from 1 up to n. And the coordinates x sub I are unique. And we write the coordinate vector for V with respect to the basis F is this vector x1, x2 down to xn. This is the coordinate, this is just what it's called, the coordinate vector for V with respect to the basis F. But we can also write V as a linear combination of the vectors in the second basis. Say yi, gi, I goes from 1 up to n. And the coordinate vector for V with respect to the basis G is y1, y2 up to yn. So if you have two bases for a vector space, every vector is a unique linear combination of the vectors in a basis. If those coordinates, the coefficients of the vectors, depend on the basis. So here is one vector that tells us how V is a linear combination of the vectors in the basis F. And here's a second vector that tells us how that same vector V is a linear combination of the vectors in G. And there is a n by n matrix P that apply to any coordinate vector with respect to one basis gives the coordinate vector with respect to second basis. So P is going to have the property that if we have the coordinate vector for V with respect to G, that's the y's. That's just written there. Sure, that's the best way. P of the coordinate vector of V with respect to G, P times this matrix times this vector will be the vector, the coordinate vector for V with respect to F. So let's see why and how this looks. Again, this is the important thing. You have a vector space of dimension n. You have two different bases, f and g, for that vector space. You have a coordinate vector for every vector with respect to a basis. So for each of these bases, you have two different coordinate vectors. And you can move from one coordinate vector to the other by multiplying by this change of basis matrix P. That's what I want to show. So we have F1 up to Fn. G is G1 up to Gn. And these are different bases for the vector space V. So for every vector in G, you can write every G sub j as some linear combination Pij f sub I goes from 1 up to n. For every j from 1 to n, you take the vector Gj, you write it as a linear combination of the fi's. So we have Pij for all I and j 1 to n, and let P be the n by n matrix where the ijth coordinate is Pij, P11, P12 up to P1n, P21, P22 up to P2n, down to Pn1, Pn2, Pnn. So let's compute what happens when you take a vector v. Let v be a vector in V. And suppose the coordinate vector for V with respect to F is x1, x2 to xn. And the coordinate vector for V with respect to G is y1, y2 down to y sub n. So V is summation I goes from 1 to n, f sub I, x sub I, f sub I. And also summation I goes from 1 to n, y sub I, g sub I. This is V expressed as a linear combination of the F vectors. This is V expressed as a linear combination of the G vectors. Maybe I'll call this GJ. So let's write GJ as a linear combination of the F's. This is summation. J goes from 1 to n. Y sub j and GJ is summation I goes from 1 to n. Pij fi. If I interchange summations, I goes from 1 to n. J goes from 1 to n. I have a Pij xj times fi. Fi is a vector. This is a scalar. So here I have V is a linear combination of the F's. V is a linear combination of the F's. The coefficients have to be the same. So for I going from 1 up to n, x sub I is equal to summation j goes from 1 to n, Pij xj. So if I take x1 down to xn, that's a vector which is summation P1j xj down to summation Pnj xj. This is exactly the matrix P times the vector, oops, sorry, this is a y, times the vector y1 down to yn, or P times the coordinate vector for V with respect to G. So if I take the G's, write them as linear combinations of the F's, I get a matrix P. P times the coordinates of V with respect to G give me the coordinates of V with respect to F. Now, so this allows me to go from coordinates of G to coordinates of F. I can do the same thing. I can write another matrix which takes me from the coordinates of F to the coordinates of G. So instead of writing each G as a linear combination of the F's, I want to write each F as a linear combination of the G's. So for J between 1 and N, let Fj be some linear combination. Let me call the coefficients Q, Qij, G sub J. So Qij, G sub I. I goes from 1 up to N. And I let Q be the matrix of Qij's. So if I have summation, J goes from 1 to N, Xj, Fj. That summation, J goes from 1 to N, Xj. Summation I goes from 1 to N, Qij, G sub I. I interchange summation, summation I goes from 1 to N, summation J goes from 1 to N, Qij, Xj times the vector G sub I, which is summation Yi, G sub I goes from 1 to N. So each Yi is equal to summation J goes from 1 to N, Qij, Xj, which means Y1 down to Yn. Just as before, you have to redo the calculation. This is Q times the vector X1 up to Xn. So if I take the coordinates for V with respect to G, that's the matrix Q times the coordinates for V with respect to F. And recall a moment ago I had in the opposite direction, the coordinate of V with respect to F is some matrix P times the coordinates of V with respect to G. And now I can observe something very nice. If I take the coordinates of V with respect to F, that's P times the coordinates of V with respect to G. But the coordinates of V with respect to G are the coordinate, it's the matrix Q times the coordinates of V with respect to F. So I take this matrix PQ times any vector, I get back the vector. And in the opposite order, if I take the coordinates of V with respect to G, that's Q times the coordinates of V with respect to F, that's Q times P times the coordinates of V with respect to G. So PQ and QP are the identity. So P and Q are invertible matrices. And P inverse equals Q. So the matrix that expresses a change of basis of coordinate vectors with respect to two bases is always invertible. And in fact, the converse is true. If you take any invertible matrix P, given any one basis, you can define another, you can construct another basis for your vector space. See how one does that. So suppose we have n by n matrices for the P and Q. The n by n matrices, which are invertible, and each is the inverse of the other, with P inverse equal Q. So PQ is the identity, and QP is also the identity, the n by n identity matrix. Let F be the set of n vectors, be a basis of the vector space V. Suppose that P, the coordinates are Pij, define a set of G of n vectors G by G sub j is summation I goes from 1 up to n, Pij f sub I. I claim G is a basis for V also. Well, it suffices to show either that G is linearly independent or that G generates the vector space. Because if the vector space has dimension n, it cannot be generated by any set with less than n vectors. So let's see, how can we do this? It's enough to show that Fi is a linear combination of the G's. So how can I use the matrix to do that? So what we know is that P, the matrix P, applied to any vector, to the coordinate vector of V with respect to G, gives us the coordinate vector of V with respect to F. So G is summation Pij Fi. You get any linear combination of the G's. You get, this is Gi is a linear combination of the F's. So you get every linear combination of the G's as a linear combination of the F's. And I want to show we can get the vector 1, 0. So, but Q is the inverse of P. So this means that QP times VG is Q times VF. QP is the identity. That's V sub G. So if I take the vector F1, the coordinate vector for F1 with respect to the basis F is just 1 and then all zeros. So Q applied to the vector F1 with respect to F gives me some coordinate vector V with respect to G. So if I take P of this, PQ F1 F is P VG. This is just F1. So the coordinate vector, so this expresses F1 as a linear combination of the vectors in G. So F1 is in the subspace spanned by G, which means G is a basis because it contains n vectors and it spans the vector space. I'm not saying that I'm thinking of explaining this as clearly as I would like, but that's good. Okay, I just need to pause for 1 minute and a couple of minutes. I'll be right back. So let me pause. All right, maybe now I'll begin to just do a few more problems on the review sheet. Some of them are really straightforward calculations. Let's look at problem 8. We have the equation 4x7y equals minus 28. And we want to write the solution space as an affine subspace. So let's see, we can do this in many, many different ways. If you solve this equation for y, 7y is 4x plus 28. So y is 4/7 x plus 4. So whenever you have a solution xy, it's going to be, x can be anything, but y has to be 4/7 x plus 4, which is the vector 0, 4 plus the vector x 4/7 x, or 0, 4 plus x times the vector 1, 4/7. We could even write this as 0, 4 plus x over 7 times the vector 7, 4. So the solution space L, it's the vector 7, 4 plus W. This is an affine space. And W is the subspace consisting of all, if x is any real number, so is x over 7. all scalar multiples of 7, 4 for any x in R. So this is a subspace. So the solution space, the affine space, that is the solution space for this inhomogeneous linear equation, is this affine space. Let's take a matrix and put it in reduced row echelon form. So this is 14C. It's chosen at random. A is 1, 2, 5. 2, 5 minus 1, 3, 1, 0. So the first entry in the first row is a 1, so we don't need to change the first row. And then subtract 2 times the first row from the second. 2 minus 2 is 0. 5 minus 4 is 1. Minus 1 minus 10 is minus 11. Subtract 3 times the first row from the third. 3 minus 3 is 0. 1 minus 6 is minus 5. 0 minus 15 is minus 15. So let's double check that this is correct. 2 minus 2, 5 minus 4, minus 1 minus 10, 3 minus 3, 1 minus 6, 0 minus 15. Here I have my second row. I want to get a 0 here, so I take the first row minus twice the second. 1 minus 0, 2 minus 2, 5 plus 22 is 27. If I add 5 times the second row to the third, I get 0 plus 0, 5 minus 5, minus 55, minus 50, minus 70. So then I have 1, 0, 27, 0, 1, minus 11, and I divide the third row by minus 70, I get 0, 0, 1. And then I have 0, 0, 1. I add 11 times the third row to the second, gives me 0, 1, 0. I subtract 27 times the third row from the first, gives me 1, 0, 0. So this is the reduced row echelon form of the matrix. This is the 3 by 3 identity matrix. Let's look at problem 16. I have the matrix A, 1 minus 2, 2, 0, 5, 6. The matrix B, which is 2, 0, 3, 5 minus 1, 2. If I compute AB, this will be this is 3 times 2, this is 2 times 3, so this will be a 3 by 3 matrix. So that's 1 minus 2, 2, 0, 5, 6 times 2, 0, 3, 5 minus 1, 2. Sorry, 2 by 3, this will be a 2 by 2 matrix. This is 2 plus 6 is 8. 5 plus 2 is 7, plus 4 is 11. 0, 0, 18. Minus 5 plus 12 is 7. I get that 2 by 2 matrix. If I multiply in the opposite order, 2, 0, 3, 5 minus 1, 2, times 1 minus 2, 2, 0, 5, 6. 3 by 2 by 2 by 3 will be a 3 by 3 matrix. This will be 2 minus 4 plus 21, 4. 0 minus 5, 0. 3 minus 6 plus 10, 6. And see, these are very different, right? I mean, not just, I mean, It's not just that AB is different from BA, the matrices are different shapes. Okay. All right. All right, maybe that's enough for today. I have a help session tonight at 7 p.m. And we'll do more linear algebra tomorrow, and tomorrow is the midterm. So, bye.
Okay, Professor, thank you.